Okay, hello and welcome to my channel. Today we're gonna be doing problem 4 set 2 from MIT OCW course 805 Quantum Physics 2. Okay, so let's begin and read the requirements. So use the variational principle to prove that any attractive potential have at least one bound state, right? Okay, so we're given some sort of guidance here. You would take v of x equal to minus absolute value of v of x. So always negative, and this is given to be piecewise continuous and negative, yeah, or never positive, not equal to 0. Okay, and we're gonna consider a wave function given is an eigenfunction. It's like alpha of x, alpha pi 1/4 e minus alpha x squared over 2. Okay, pretty standard. Show that the e alpha can be made to be negative with a suitable a. Okay, table is very shaky. So e alpha equal to integral dx alpha h sine alpha with h equal to 2m x squared x. Find a bound state, a bound for an arbitrary attractive v of x. So by finding x0, where the potential is continuous and negative, so you're gonna define you define absolute value of v at x naught equal to minus or equal to 2v naught. This is greater than 0. Okay, so now we consider a finite interval x1, x2 about x naught, meaning that x naught is inside. You're also given that x2 minus x1 is equal to delta. So we know that we have to use that. For which absolute value of x, v of x is greater or equal to v naught. Then we explain how the v of x can be bounded by taking v tilde of x. This is equal to minus v naught when x is inside the interval, equal to 0 elsewhere. You can see that these are attractive potential, meaning that they have a negative value. They pulled stuff in. Okay, so let's begin by calculating the kinetic and potential value, the expectation value of these two things. This is p squared over 2m, and you see that this function is identical to what we did before in previous videos. This is equal to 3 over 2 h bar squared alpha 1 over 2m this is equal to h bar square alpha for m. So if you want to see the detailed step-by-step solution to the 3 over 2 h bar square alpha, you can check out, I believe, problem 1, set 1 that I did a while back. Okay, now we have this, and following the guidance here, saying that exists an x naught inside the interval x1, x2, where our absolute value of v at x naught is equal to 2v naught that is greater than 0. Okay, and also define v tilde of x to be equal to minus v naught when x is inside the interval and 0 elsewhere. Right. Here you have this. You can see that the absolute value of v at x naught inside the interval is 2v naught, meaning that, well, it is negative. So v of x here is less or equal to v tilde of x, and these both have to be equal to or less than 0. These are attractive. Right. So from here you can get that their respective expectation value also follows the same as above. So expectation value of v of x is less or equal to the expectation value of v tilde of x. Okay, so now we have this. Let's try and evaluate each of these. Take v of x first. This is integral v of x of psi alpha square dx. Okay, maybe, oh yeah, we're gonna stop at this first. There are not much to expand anyways. Let's consider the next one. Minus v naught. Minus v naught can be factored out. This only exists inside the interval, meaning we only integrate over the interval dx. Okay, so yeah, let's leave it at this first. Okay, so you can see that these two, they have a different range of the interval, but we're gonna compare them two because the limit of both of these to plus minus infinity is 0, so we can technically compare these even though they have a different range of integral. So this is a pretty confusing part because you have to compare these two, which basically have the different range. Alright, so alright. If this still holds. Next we're gonna be finding a bound, meaning we're gonna take a maximum of something of x here. Okay, so we're taking say maximum. Take a Vmax. No, yeah. Let's take a Vmax of x to be proportional to e minus alpha square x max. Okay, now let's try and compare these two. So of course, the x max, the expectation value of x max is gonna be our upper bound. X is v max of x. So we can write it this way. Now we can start to expand our integral here to find what we need, since we can't really go much further without doing so. Okay, so this one, this to fourth bring out, that is alpha over pi roots. Then we write again the integral x1, x2, that join with a square, so only minus alpha x squared remain. Okay, so this is for our v tilde. Next is, let's evaluate our v max of x. V max also in the interval, so also minus this x1, x2 dx sine alpha square dx the square max. We're taking x max. So this is minus v naught, same, alpha over pi roots, same. We're taking x max, so we can write delta here, because, well, you're integrate in this interval, but x max is not exactly in the interval, so you can treat x max as a constant, so you bring the whole thing out, so e minus alpha x max squared, and then you're left with integral x1, x2 dx. This is x2 minus x1, this, so equal to delta. Let's see, to delta. So you got your upper bound for your potential. Now we can join and write our energy. So from 1 and 2, you get that your E alpha, where was it? What did I write? E of alpha has to be less or equal to h bar square alpha for m. This is minus v naught delta alpha pi roots e minus alpha x max squared. Okay, so we got this, and this is when we're gonna try to manipulate this to get something that we want. More specifically, we're gonna take alpha to go to 0, because now when alpha goes to 0, the root alpha term is gonna be the dominant term. You can think of it as like alpha squared and alpha. So more specific is like 0.005 square is of course less than 0.0005. So we're going to apply this to the above. We're going to get that the root alpha term is going to be greater than the alpha term, and the exponential term when we take alpha to go to 0 is going to equal to 1. Therefore, seeing the dominant term has a minus sign before it, our E of alpha has to be less than 0. Right. So with this, we can say that, well, by variational principle, our ground state energy, of course, has to be less or equal to E of alpha. And therefore, what we need has been proven. Any attractive potential have at least one bound state. Right. And that's it for today. Goodbye.